Hello, my name is Dimbinaina Ralaivaosaona. I'll be talking about the probability that a random digraph is acyclic. This is a joint work with Vonjy Rasendrahasina and Stephan Wagner. This is a picture of the three of us. This is me, this is Vonjy, and this is Stephan. We consider digraphs on vertex set 1 to n, where loops and multi-edges are not allowed. A loop is an edge that come from a vertex to itself, while multiple edges are edges going into the same direction. This is not a multiple edge. This is not a multiple edge. We call this a two-cycle because the edges are going in different directions. The following models will be mentioned in this talk. So we're talking about the first model where we avoid two cycles. So how do we obtain the random digraph in this case? So we generate an undirected graph according to the binomial model with binomial model GN2P. So there's a 2 there. And then we choose a direction of probability a half independently of any other edge. The second model is where we allowed two cycles. We choose each possible n times n minus one possible edges can occur independently with probability p. In this work, we want to determine the probability that the random digraph in the first model is acyclic. That means there are no directed cycles. Although in this talk we talk about the first model, it is also possible to translate our result in terms of the second model because our method is based on the enumeration of acyclic digraphs. We're primarily interested in the sparse regime where p is equal to lambda over n, where lambda is bounded. Okay. Some properties of random digraphs. Say the model DNP, the second model, exhibits a phase transition similar to the model GNP, the undirected graph model, that is based on the result of Karp and Uchak. So you have your subcritical phases where your components are small, and you have a critical phase and a supercritical phase where you have a giant component. Although nothing much is known in the critical window. If we look at the statement of the results of Karp and Uchak in the 1990, they obtained the first theorem where p is equal to lambda over n, and lambda is fixed, and you know lambda equals to 1 is not here. More recently, Uchak and Sierstad obtained a result in the critical window, just outside the critical window. All right, so NP equal to 1 plus epsilon, where epsilon tends to 0 but satisfies this property. So nothing much is known in the critical window itself, and we hope that our result here can lead to some understanding of what happens in that critical window. All right, the first model also appeared. Subramanian studied induced acyclic subgraphs in that model, and some other papers appeared as well. A paper of him with Spencer and Duta as well. As I mentioned earlier, our method is based on the enumeration of acyclic digraph. This was studied extensively in the past, so in the 1970s, or perhaps even just before. Liskovets had a paper in 1969, but also Harari, Palmer, 1973, Robinson, and Stanley. So what happens is that if we denote by an the number of acyclic digraph on n labeled vertices, then an satisfies this recursive formula, which is based on inclusion-exclusion principle by distinguishing the number of sources or sink in the acyclic digraph. The initial value here is a naught, so you can get the sequence of an starts like this, and it's in the online encyclopedia of integer sequence. So as you can see, it grows quite fast. So in order to study this, we consider generating function. The generating function for DAGs, you consider something called graphic generating function. So you have a generating function, but there is a term 2 to the power minus n over 2, n choose 2. So based on the recursive formula, one can show that the graphic generating function satisfies this property. It's 1 over phi x, where phi x is the special function here. Okay, it's very similar, but there is no an in there. All right, so clearly phi defines an entire function, so and it has a simple 0 around this point here, and that allows you to extract the coefficient of your graphic generating function, and you get your asymptotic formula for the number of acyclic digraph on n vertices. This result appears in Liskov-Etz in 1973, Robinson in the same year, and Stanley. Okay, it's not difficult to include the number of edges in the count, so you consider a and m to be the number of acyclic digraph on n vertices and m edges. So the only difference here is that 2 becomes 1 plus y, and then you get everything similar to the one before. We have a version of the function phi, and once again, instead of 2, you get 1 plus y. And it still satisfies the same functional equation, so axy is 1 over phi. So Bender, Richmond, Robinson, and Wormwald in 1988 obtained an asymptotic formula for a and m, so number of acyclic digraph on n vertices with m edges when m is quadratic in n, so that's dense acyclic digraph. That's one of the motivations why we consider sparse digraph. This was done by studying the zeros of phi when y is positive and bounded away from 0, obviously, so you try to look at the 0 as a function of y. So talking about the zeros of phi, it is known that they are real and positive and distinct, right? This is discussed in that paper of Bender and al. So in this figure, we show the function phi for several values of y between 1 and 0. In particular, when y is 0, you get the exponential function, and that's never 0. So as a result, one could think of the zeros of phi to tend to infinity when y tends to 0. So the question is, how fast do the zeros tend to infinity when y tends to 0? And that's our first result. So we show that the J0 of phi satisfy the asymptotic formula here. So for J fixed. So they all have the same main term, but and that's of the form 1 over e, so 1 over e times y to the power minus 1, but they differ in the second term, which is of order y to the power minus 1/3, and the difference is a constant here, aj, where j is the J0 of the Airy function. We also obtain the derivative of phi at these zeros, which is important for the enumeration purposes. Using that result, we were able to obtain the following in terms of the probability of the random digraph is acyclic. So if p is equal to lambda over n, where lambda is fixed, then we have the probability. So the probability that dnp is acyclic, if lambda is between 0 and 1, then we have this function of lambda here, which is a function that goes from 1 to 0. In the critical phase, when lambda is 1, then we have this function, which is a polynomial in n, so n to the power minus 1 over 3. And when in the supercritical phase, we have the appearance of exponential function. So the constants are all written here, but they involve the Airy function. The first part here can be done without the analysis of the function phi. So I'm going to leave that out in this talk. So I'll be talking about the critical and supercritical phases. Looking carefully in the critical window, so that's when NP is equal to 1 plus mu times n to the power minus 1 over 3. When mu is bounded, then you can then the probability is still polynomial in n to the power minus 1 over 3, but multiplied by a function phi, curly phi mu, where phi is given by this formula. The area function, there is an integral of reciprocal area function here, which is a inverse Laplace transform. Okay, so the function phi has the graph of the function phi looks like this. Okay. So why does the probability has anything to do with the zero or the behavior of the function phi? It's because of this lemma here. So the probability that the random digraph is acyclic can be written in terms of the coefficient of the graphic generating function, where y is equal to p over 1 minus 2p. So how do we go about proving something like that? Well, you start by writing p. So p is equal to the sum, so sum over the edges, and you take all the cyclic digraph on n vertices and m edges, and the probability of getting one of those is this. So you choose the m edges, so that's 2p to the power m, because remember we are generating the undirected graph gn2p. So choosing the undirected edges, that's 2p to the power m, and not choosing the rest, that's 1 minus 2p, and choosing the direction for each existing edges, that's 2 to the power minus m, and just manipulate, and you have the sum, and the sum can be written in terms of the coefficient. So here the coefficient has the same sum, y just have to be equals to p over 1 minus 2p. So that's the reason why the probability can be obtained in terms of the property of phi. So all we have to do from now on is to extract the coefficient of the graphic generating function when y is equal to p over 1 minus 2p. So how do we do that? Well, we need to obtain asymptotic formula for phi x. So phi is written in terms of sum. However, Mahler, using something called Mahler transformation in Mahler's paper dated in 1940, we can write phi in terms of an integral, which is given here. Mahler obtained this by studying his partition. So this can be written in here, where in this form, so integral of exponential f of z, where f is written here. So from now on, it's convenient to write alpha equals log of 1 plus y and beta equals square root of 1 plus y. So we use the saddle point method to estimate the function phi. And what we do is we take the derivative of f and equate it to 0, and we have this equation, and clearly we get the Lambert function. The solution of this is in terms of the Lambert function, and since the Lambert function has a singularity of minus 1 over e, there is a special case here when the right hand side is equal to that number, minus 1 over e, then something special happens. So that happens when x equals x naught is equal to when x is equal to x naught, and the solution of this equation is just I. And if you do, then at that point you have a double saddle point. So f prime at that point is equal to f second, and both are equal to 0. So what we do then is to consider x to be around that special point. And so what we do is, well, we consider x around that special point, and we calculate the saddle point, the solution of this equation, we name that to be Z0, and we apply the following trick. So if that Z0 is close enough to I, if Z0 is far away from I, then we take the path of integration, which is just a horizontal line, which is allowed because the integrand of our integral tends to 0 very fast on a horizontal strip. But if it's very close to I, so if Z0 minus I is of order alpha to the power 2/3, alpha is about y, then we take this path of integration, which is again allowed because the function is entire, so we can move the part of the curve. So this is the reason why the Airy function occur in the estimates. So using this, we get this, which is complicated. Let me just help you read this. So the first two are for values of x before that special point x0. So far away before, these are the estimates of phi. And if you look at them very carefully, they are never 0. So this is an exponential function, that's never 0. Here's an exponential with Airy function, okay, but Airy function of something positive, so that's not 0 either. But if you just passed, so when delta is about theta times alpha to the power 2/3, where theta is 0, then phi is about this much, okay? Then you look at the main term, that's Airy function of something negative, so minus 2 to the power 1/3 times theta. And that can be 0, and you can get the 0 out of that by using a bootstrapping argument. So now to get the probability, we just need to extract the coefficients of our graphic generating function. And the previous idea can be applied to complex values of x. So here, in particular, if we take x equals x0 times exponential it alpha to the power 2/3, then you have this asymptotic formula here. And the difference, of course, is that there is an Airy function here of minus I t. So in the critical phase where NP satisfies this, recall that y is equal to p over 1 minus 2p and alpha is equal to log of 1 plus y, then we can get n in terms of alpha, and we deduce that the coefficient of the graphic generating function satisfies this this form here, and you see the integral of reciprocal Airy function occur. All right, so to get this formula, you apply your Cauchy integral formula and choose a circle that is just before the first 0. Okay, so we choose x0 here, and the main term comes from the part in the circle, and that's why this term appears. Okay, in the supercritical phase, we choose a circle of radius. To extract a coefficient, we use the Cauchy formula again, but we choose a circle that is with radius between the first 0 of phi and the second 0 of phi. Then we can use Cauchy residue theorem, and the main term would come from the first 0. Okay, we can calculate that the second term contributes very little. And that's how we proved our result. Here are some simulation. So the first one is the sparse, and the three others are in the supercritical phase, and then you see the cycles in red. Here's a Monte Carlo simulation to approximate the function phi in the critical window, and you see it fits really well. So what next? So the long version of this paper is already available on arXiv. It contains a lot more things. So we consider 3 different models of random digraphs, including the 2 I mentioned here. We considered different parameters, different properties. We consider the probability that the random digraph is acyclic, like the one I just talked about. The probability that the random digraph is elementary. That means that the strong components are either single vertices or cycles. and we also consider the probability that a random digraph has one complex strong component. And this is a work with the authors of the present work plus Elie de Panafeu and Sergei Dovgal. We can also look at the parameters of random acyclic digraph. For example, what would be the number of sources and sinks, and we think we could also include that in the future. Thank you.